So I will review shortly what I finished yesterday. So we considered this expression. We take the Wasserstein distance between two distribution G1, G2 with a small parameter epsilon. And so we take the distance between actually the probability measure mu to itself, but perturb between a pair of probability distribution G1, G2 in dimension 1, and we get the approximation that for small epsilon, it is approximated to leading order by this integral. I want to give you some more intuition about it. When you have the Wasserstein P, and you have two distributions, say, between two distributions, nu1 and nu2, and if you add the same measure to both sides, the same measure for both sides, you can really observe that this will decrease the cost of transport. Not in if you add something. Why? Because if you look at the optimal map which transport nu1 to nu2, yeah, and then you add some mass to the domain, you can use the same transport mass which push nu1 to nu2 and leave the other mass at rest. So this will have the same cost as the distance between nu1 to nu2, but this will not be optimal. You can have much better if you calculate the optimal transport. And in fact, if you increase the mass, so multiply it by some big number m, and let m goes to infinity, the cost will go to 0 in general. Yeah. Well, unless mu has some gap. So suppose that nu1 is something. Nu1 and nu2 are two distributions which has a disjoint support. And mu is some measure here, which somehow bridge these two. In this case, if you multiply mu by very large constant, the cost will go to 0 as m goes to infinity. But if the measure mu has a gap inside, so here is somewhere here, it will be 0, then the cost of transport from here to here, so I want to transport now this plus this, so mu plus this, the cost of transport, the transport will have to jump this gap, and you will have to pay something which is proportional to this distance. So this will not go to 0, even when m go to infinity, it will go to the distance between these two, the distance of the gap between two parts of mu. So I can, what I considered here is I scaled it in such a way that mu is a probability measure, and I put epsilon here, and you see that in fact, here is WP to the power P, which is actually, we have to put WP to the power P to get the cost, because the cost is x minus 1 to the P. So in general, we expect it to be like order of epsilon to the power, the distance between epsilon G1 to epsilon G2 is something of the order epsilon to the 1 over P. But here, because of the mu, it's of order epsilon. And we get this expression. And the next thing that we claimed is that if we ask what is the, excuse me, this is wrong. I have to put it minimum, not maximum, sorry. The minimum of the cost of transporting G1 to G2, the mu which minimizes the cost, it turns out to be just this integral, which is the L1 cost of transporting G1 to G2. By the way, if P equal 1, then this mu doesn't change anything. Why? Because you will recall that W1 is, by duality, it is supremum over the integral of phi d nu1 minus nu2 over phi in lip 1. So it's only a function of the difference. It's a norm. It's not, this metric is a norm. It's only dependent on the difference. So if you add something to both sides, it will not change it. So here is a sketch that expresses this phenomena. Here I put some delta mass here at point x1, and then delta mass at the point x2, and I want to push it distance L. So I pay L times this mass. So suppose the mass is epsilon here and epsilon. I pay L times epsilon for W p to the power p. And if I have a uniform, I pay just epsilon to the power p because I can push it step by step. So I take this block, move it epsilon distance to the right, and then another epsilon to the right, and so on until I get here. And each step I pay epsilon to the power p. And excuse me, I pay I move it a distance epsilon, so I pay epsilon to the power p, and I do it 1 over epsilon times, and take the p root, so I get the power epsilon. And if the distribution is not uniform, then I have to make bigger steps. So I have to pay more, but still the same order. What happens if epsilon is positive, not going to 0 in this limit? So I again consider two delta function, Dirac delta function, one at 0 and one at 1, say, and I add m times mu to both sides. And I prescribe m, not taking it to infinity. So what happened here is that if I try to substitute mu as a discrete measure, and if m turns to be an integer, then it turns out that an integer k, so mu is just distributed equally along the line connecting 0 to 1 at distance 1 over k. So the cost is 1 plus k, 1 over k. If m is not an integer, there's integer plus some alpha between 0 and 1, then the rest of the mass is distributed between the grid of 1 over k and to grid distance 1 over k plus 2. So the optimal cost will be this one. Anyway, this is just a thing that we can check by direct calculation. And of course, as n goes to infinity, this measure converges to uniform measure on the interval between 0 and 1. So to conclude our discussion on the one-dimensional transport, I want to consider a map on a circle. So there is a paper that I can write now the reference for if somebody is interested. It's called the rotation numbers. For measure valued circle map. Which published in the Journal d'Analyse. In 97, this was in 2005, old paper. But still, I think this is a kind of amusing example. Where did I put one? Oh, yeah. So on the circle, we can consider the circle to be R mod Z, R mod 1, and we can consider the cumulation function to be a function from the real line to itself, which is monotone, which has this property. Whenever you increase the x by 1, you get the same value plus 1, because this is the lifting from the circle to the line. Of course, the way we define the cumulation function, which was the measure mu between minus infinity to x, here we have a periodic measure, so we have to define some point to start here, and this point is arbitrary, so it's defined only up to some constant w, and the inverse is also defined up to some constant shift in the parameter x. So the WP, the Wasserstein distance between two measures mu and nu, is given by, on the line, it is just the P norm of the x mu minus x nu, but here we take the minimum of all shifted x, one of them, for example, say x mu, we take the minimum of all shifted x mu to get the WP norm. The reason is that the distance on the circle is not just a clear distance. This is the distance between 2 points x and y in a circle is the minimum of x minus y plus k, the minimum of all k in Z, right? So this is the distance we use on a circle, and this leads to this variation on the definition of the Wasserstein distance on the distance with this cost function. So if we consider a map from the circle to itself, we can lift it to a map on the real line, which satisfies this tx plus 1 equal tx plus 1. And then we define a rotation number associated with this map as this limit. So we take an iteration for the point x on the line. So it moves along the, it jumps from point to point on the real line and take the limit divided by n. And this is independent of x, you see, because if you take 2 points, x and y, on the unit interval, which represent the circle, then the distance between t and x and t and y is just at most 1. So in the limit, that doesn't depend on x. So now suppose we have a family of measure which makes a periodic orbit on the circle. So this is this is a 2 period. So the periodic with t. So mu of t is the same as mu of t plus 1, and it's a measure on the circle. So we want to associate. So I want to ask, can we obtain a rotation number for this? So let us consider a very elementary case where mu t is just an orbit of a delta function, one particle. So suppose mu of t is a delta function concentrated on orbit x of t, then x of t is a periodic orbit of the circle, so x of t plus 1 equal x of t plus d, and d is as d is an integer. And this integer is the index of this orbit on the circle. It measures how many revolutions it does per period. So of course the rotation number for this mu will be just d. Yeah. But what happens if we have mu of t composed of a combination of orbits like this? So suppose u of t is 1 over n sum of delta xit. And each xit has a degree, may have different degree. Okay. We should find out that we really can define a rotation number here. The rotation number, not surprising, will be just the average of these rotation numbers. And if you ask what is the meaning of this, so imagine that we have some people running on a circular ring, and one of them is carrying a flag. So people are running, each one each have a different velocity. Each one has after one period, each one complete an integer number of rotation. And whenever this runner, which carried the flag, cross another of the runner, he gives him the flag. So if you follow this flag and see how many revolutions the flag is doing on the average after a long time, then we see that this is just the average of the rotation number. Later I saw such a question in the mathematics Olympiad, but I don't think that they meant to solve it in this way. Anyway, so we want to see if we can assign a rotation number. And for this, we want to find a mapping corresponding to this flow of measure mu of t. So you remember we have to assign a velocity. We have to look for the continuity equation. So if rho is the density of this measure, and in a one-dimensional, we consider this equation, but if we integrate it on x, so integrate from this equation with respect to x, so the integral of rho is f, so we get f t equal v, excuse me, plus v f of x is some function which of t. When we differentiate it, remember that d over dx f equal rho. So this will be just the integral of this continuity equation. So we can so we can factor out v. The velocity will be this. So we want to find the metric derivative. Remember, the metric derivative is just the integral of just the metric derivative with respect to the Wasserstein 2 is the minimum. Now I denote it by this. Actually, yesterday I defined it like mu dot, but the same thing is the minimum of the integral of v square rho, minimum of all velocity field, which is compatible with the with rho on with the continuity equation. So here we take the minimum. We know v up to a function lambda of t. So we take the minimum over all possible function lambda of t, and this is rho. So this is v square. What's in the brackets is v square. Fx is rho, so v square rho dx dt. And we take the minimum or lambda. So f square is reduced here, and so we can easily obtain that the lambda which gives us the minimum is just this quotient, the integral of ft over fx over 1 over fx. So 1 over fx is 1 over rho. So what is this? Is just the average of the function, a combination function derivative by t. We average it with the mass rho minus 1 over rho. That's the integral of df dt times 1 over rho over the integral of 1 over rho. That's precisely the average with respect to the 1 over rho. So this is the velocity field. From here, this is just 1 over rho times the average of ft minus ft. Okay? This comes out from this. Okay. Now, I want to calculate the rotation number. So I say, well, if I differentiate df over dt, so we differentiate with respect to the first and second variable. So the first variable is fx times x dot plus ft, but x dot is v, and I substitute v here. And so I get that if I substitute v from here, I get immediately that this ft is cancelled, and what we are left is just this one. So we are left is just this. What is left is just this term. So this is the derivative, the complete derivative of the cumulation function with respect to t, just the rho minus one, the average with respect to rho minus one of the FDT. Now, the distance between ft and the orbit of particle xt is two periodic. So it's period. It has a period one with time and one with x. So it's bounded. So if you want to look at the limit of the orbit xt over t on the line, this will be the same as this limit, right? Because the difference between f and x is bounded. So because this is a periodic, this is like the average of, this is equal to the average of the integral over t of the rho minus one average of t. So let's look for example. The first example is rho is just as a constant profile shifted by a function x of t. So we have imagine some fixed distribution of particles, and they move as a rigid body along the orbit xt. G, it should be rho. So rho is positive, and the index of this orbit will be d. Yeah. So if this was a delta function, we already saw this will be just d. This is the index of x. But what happened in this case? So we can write for f of xt, we can take the primitive of g, and f of t will be just f of x minus x of t minus f minus xt. This will be f, which is normalized such that it will be zero along the orbit. We can normalize f, we can decide whenever we want the zero of f, because we saw that it's defined only up to shift constant. So we choose f to be zero on the orbit x of x of t. And then when we take the average, we get, we take the average of f with respect to 1 over rho. We get this thing. This is the velocity of this particle, of this shift, times this difference g at minus xt minus 1 over the integral of 1 over g. Now d, what is d? D is the distance that x travel at unit time. So it's the integral from 0 to 1 to x dot. But this is also the integral of the gdt. So this, because g is moving, g calculated at the point x, because g has a period 1 in x. So the same as the integral of the gdt, and the gdt is just, the integral of the gdt is just this integral. So what, so we obtain that the rotation number is, which is this integral, is just d times 1 minus 1 over the integral of 1 over g. So you can see if g has some zero, so if the profile of g, the moving profile, has some interval 0, then the integral of 1 over g is infinity, and the rotation number will be d. That's that's kind of obvious because there is a gap that's moving around with the speed of xt, and particle cannot jump across this gap. So they follow the velocity of x dot. But if g is positive everywhere, so the integral is smaller than 1. Obviously, the integral of g minus 1 is always bigger than 1 because Jensen inequality, the integral of g is 1, right? So this number is between 0 and 1. So you see that when you have g which is positive everywhere, you get rotation number smaller. Yeah. For example, you can imagine that if you have, so if G is something like you have almost a uniform, have a small bump, and this small bump move with a fixed velocity, the speed of the velocity of the fluid will be small, because if there's even if the bump is moving very fast, the velocity of the fluid will be small according to this formula, because the integral of 1 over g minus 1 is almost 1. So you can also see that this rotation number is not continuous in the vector topology. So far, I assume that everything is smooth and strictly positive in order to get this formula. The question is, can we take the limit, weak limit, to obtain general measures, measures of general orbits of measures. So obviously, R is not continuous in the vector topology, but turns out that it is continuously we define this topology over the orbit. So what is this topology? We have two paths, mu1 and mu2, and we they have velocity w1 and w2 respectively. No, we have velocity v, yeah? v1 and v2. So we define w to be the velocity field shifted according to the map T, which the map T is the optimal Monge mapping that push the Lebesgue measure to the measure mu T at time T. So for each time T, we define this W as the velocity field with this variable, with this change of variable, and take the L2 norm of the difference between these two velocity field plus the uniform distance between the Wasserstein two distance between the two measures. With this metric, turns out that the rotation number is continuous in the Wick topology. In the Wick topology, defined by, in the topology defined by this metric, and if you take the space of smooth densities and complete it with respect to this topology, you get the whole space of Borel probability measure, which has a finite metric derivative in L2. Okay, and then we can find rotation number for any measure which has a finite in L2 metric derivative. So, for example, if you look at a measure which is a weighted combination of a delta function along orbit xit, again, we get the rotation number will be beta I di, where di is the degree of each of them. And I don't know how to interpret this, maybe because if all the beta I are equal, so that was the case that I described before, like the runner on the, like a relay race on the circular ring. But if beta are not the same, then maybe there is some stochastic process which we associate with that. When a runner gives the flag to the one who crosses it, or don't give him according to some probability, depending on the ratio between the constant beta I. So here is the proposition on the smooth of one periodic probability flow S1. They are dense in the D topology. So this is the D topology. In the set of all orbit, which has a finite L2 norm in the, whose metric derivative has a finite L2 norm. And it's in a Lifshitz. So the difference between two rotation number is bounded by the distance, D. So it's rotation number is a Lifshitz function. Constant one with respect to this metric. Okay. So this, in the meantime, conclude our discussion on the one-dimensional transport, and I want to return to the general dimension, but say something on the case of a metric cost. Metric cost means this is the W1. Yeah, we want to study the case of Wasserstein distance 1, which is a special case. Special case because that you call this is a norm, and it has to do with the Lifshitz functions. So so many people work. The first one who worked get the result of this was Sodokov in '76, and then Ambrosia, Gigli, can find the reference there. And the theorem that need to be proven is that first, if omega is a compact subset in RD, and U is absolutely continuous with respect to the bag, then there exists a transport map T which realizes the infimum of the Wasserstein 1 distance. And it's generally it's not unique. Like I mentioned before, the book shifting. Let me remind you again what it is. For example, we have a shelf of books here, and we want to move it one book to the right. So we want, there's one book here. We want to push all this line one to the right. So we can do it, we can take the first book and put it here, or we can push all of them one to the right, or we can just take one of the book in the inside, put it here, and push from here to close the gap here. All these transports are the same, give us the same price in W1. If you just measure the distance in the power 1 as a cost. So we have no uniqueness, but what we saw, I think it was yesterday or before, that there is a unique transport which is monotone on the line. So I also remind you the duality condition that is the supreme of all Lifshitz function 1, which maximizes this, the mu minus the nu, and the Kantorovich potential mu, which maximizes exists. And it is supported. This is from the general theory we know about from duality. It is supported on the points x, y, which satisfy this equality. So the distance, ux minus uy equal precisely x minus y. All these pair of points contain the support of the optimal transport. We know the optimal transport measure exists, and we know that its support is contained in this set, the set of all points x, y. So we call it set A. Later I will write it now. So A is the set of all points x, y in omega, such that ux minus uy equal. And this is contained the support of mu, of gamma. Gamma is the optimal transport. So we want to see if we can define a map which almost everywhere, almost everywhere, which take which is on which the support of gamma lives. Yeah. So let's see what we can say now. Suppose there are 2 points like this, ux minus uy equal x minus y. So u is a nothing function on the interval. So look at the interval connecting the point x to point y. So for any point in between, tx plus y minus ty is equal to should be tux plus y minus ty, okay? So because let's see. So this is point x, this is point y, and let's put x1 and y1 here. So if we consider uy minus ux, we know that's y minus x, and this is equal to uy minus uy1 plus ux1 plus uy1 minus ux1 plus ux1 minus ux, and this is smaller equal than the absolute value here. So uy minus uy1, because if it's 1, it's smaller equal to y minus y1. And this is smaller equal than y1 minus x1. And this is smaller equal than x1 minus x, absolute value. But on the other hand, this so I want to prove here. What did I want to prove here? No, that's not what I want. Sorry. So we take this distance, this distance, this distance. So the sum of this distance, of course, is the distance from x to y. So what I want to prove is that u y1 minus u x1 also equal to y1 minus x1, or any 2 points in the middle of this interval, if we satisfy that xy is in the set A. So so this should follow easily, right? Just by triangle inequality, but okay. Let's leave it for now. We should try it later. Anyway, so we have this fine connection between x and y for any 2 points in the interval. So, and the second statement is that u is differentiable at any point in the interior of this interval, x and y. And the gradient of u is just the x minus y over the absolute value of x minus y. So this statement is an exercise in calculus, but it's very important for the proof side. Let me give you a proof for this. So what we want to prove, we have this line, call this direction E. So E is the unit vector y minus x over y minus x. So let's take a point Z. So this is x and this is y. So let's take a point Z on this interval. And let's take a point Z prime prime somewhere in the plane. So what we want to prove is that u, the point Z prime prime, minus u at Z is equal Z prime prime minus Z multiplied by E plus small o of Z minus Z prime prime. This will say that u is differentiable at Z, right? So this is what we want to prove. So let's prove it. So let's take, let's call this point Z prime. This is the projection of Z prime on the line, and this direction called H. And H is a unit vector perpendicular to E. And H is y. So Z prime prime is actually Z prime plus TH. T is some number. And let's fix some number T0 and consider these 2 points. This is Z prime plus T0E, and this will be Z prime minus T0E. Okay. And then we make the following estimate. We calculate u at Z prime prime, which is Z prime plus TH, minus u at Z prime minus T0E. So we calculate the value of u here minus the value of u here. So we write it like u at Z prime plus TH minus u Z prime plus u Z prime minus u Z prime minus T0E. So, okay, let's call delta the difference between here and here. So delta will be u at z prime plus th minus u z prime. This is the number delta. So this is delta. And this distance is just T0, right? Because this would be along this line, the distance, the difference between ux and uy on a point is just, at any pair of points is just the distance along the line. But on the other hand, this is smaller or equal from t square plus t0 square, right? Why? Because this is the length of this the hypotenuse of this right triangle. So we know that u is Lifshitz 1, so the distance between value here and value here is smaller than this distance. And by Pythagorean theorem, this is just t square plus t0 square. The same thing if you calculate the distance between u minus u at the second point, the point here. You do the same thing, plus T0 here. And the same calculation will give us that this is, well, I can do the same calculation and I get this is delta minus T0. This is again smaller or equal than square root of T0 plus T0 square. So of these two inequalities, we take, we square both sides, so we get that t square plus t0 square is bigger or equal than delta plus minus t0 square. So this is delta square plus minus 2 delta t0 plus 2 0 square. So we raise t0 both sides, and what we get is that plus minus 2 t0 delta smaller equal than t square minus delta square, which is smaller equal than t square. So this is true for both plus and minus. So delta is smaller or equal than delta. The absolute value of delta is smaller than t square minus 2 t0 squared minus 2 to 0. And anyway, this is small o of t. Right? That's what we wanted to prove. That the delta, which is the value between the difference between u at here and u here, is a small o of t. So now when we calculate the distance between u here and u here, to the other side, so u z prime prime minus u z is u z prime plus th minus u z prime plus u z prime minus u z is z prime minus z dot e plus O of t square, and z prime minus z dot e is the same as z prime prime minus z dot e because this is the projection on the line, E is the direction of the line, plus O of t square. And of course, T is Z prime prime minus Z. So we get differentiability of U at any point, at any interior point on the interval. Okay, so when we have this result, we can now move to see the geometry of this business. So we can look at interval, what we call transport rates. What is the transport rate? For each 2 points in A, for which this equality holds, we consider the maximal interval containing the segment between X and Y on which this equality holds. So there may be an interval, the finite interval, for all these points on this interval satisfy this condition. And this also defines an order on the interval, right? Where we can say that point Y is higher in order than X if X is higher order than Y, if U is increasing, if Ux is bigger than Uy, and the difference is X minus Y absolute value. So we define the transport race. So we can split the whole space into transport race like this, and the end point, we call it transport boundary. So this is a transport ray. This is the maximal transport ray. The boundary will be, this is the maximal interval on which this equality exists, and the transport B is just the endpoints of this interval. And the B plus, so trans B plus is the set of all points, the higher endpoints of this interval, the points for the maximal U. And the transport B minus is the lower endpoints of this interval. So this would represent a family of lines and points in the domain omega. Transport rays must be disjoint, right? They can only meet at the endpoint. Why is that? Because if they meet in the interior point, it means that at this point we have two different gradients, right? Because the gradient always of an interior point always point in the direction of the ray. So it cannot be, but we know this is differentiable, so they cannot meet inside. They can meet at the endpoint of the maximal interval only. But we know that U is Lifshitz. So the set of all non-differentiable point of view are negligible in Lebesgue. If we remove this negligible set of non-differentiability, we still have a set which is a full measure. Let me just skip one page. So what I say here is that in this set A, we can distinguish four cases. The first case is the singular U, that's all points which are not differential in U, which this has a Lebesgue measure 0, points which are not on transport ray. What does it mean that point is not in transport ray? It means that there's no Y equal to X. So the two endpoints of this interval shrink to 1 point. points in the transport in the end of the transport ray, which are not singular, means that also x equal to y, and all the rest of the point, which is in the interior of the transport ray. Let me repeat again. Take any pair x and y in gamma, in the set which is a support of, which contains the support of gamma, which is contained in A. Gamma is the support of the optimal measure. And for any point x in this pair, we consider the points y along this ray. So if x is in the transport ray and not in the singular set and not in the endpoint of this interval, then y must be bigger equal than x. What does it mean bigger equal to x? It means that uy bigger equal to ux. This is the and along the optimal transport gamma, okay, okay, so I have to come back and define what is CA. So we recall that in general there's no uniqueness, but there is uniqueness for monotone mapping. So we want to discard all planes which are not monotone in this sense. So let's define a secondary problem. So I look for a cos C, which is quadratic, but it's only quadratic on the pair x and y in the set A, and infinity otherwise. And I minimize the cost between mu and nu with respect to this cost. So this cost, so the infimum is actually live in the set of optimal measure, right? Because we know that any measure supported in A is an optimal measure, but the one which reached the infimum with respect to the quadratic cost is would be a unique one, because this is a strictly convex. So if we look at now the gamma, which is optimal with respect to this distance CA, so in particular, this optimal transport for W1, and this is because as we said, it's Katarovich potential, and also CA is our semi-continuous, so gamma is supported in a CA monotone set containing A. Maybe not closed one because CA is not continuous. So if you have pair of points x1, y1, x2 in gamma, or on some transport ray, then we have this inequality, which is just the cyclic comes from the cyclic monotonicity, which we know for the support of optimal mapping. So it turns out that all pairs in the set gamma is supported on a graph of monotone multivalued function. Yeah, this is say that if x2 is bigger than x1, then y2 is also bigger than y1 when we consider it along the transport ray. So what happens when we have a monotone map? So let's say this is a monotone map. It may be discontinuous at some points. this. At the point of discontinuity, map is not defined, right? Because any point along the transport ray for which there is a discontinuity gap when the y from the left jump, y from the left jump to the right, then we have no one-valued map. But there can be at most countably many points of discontinuity on a monotone map, right? On a monotone function, right? On the line. So along each transport ray, there are at most countably many points of discontinuity. So these are the bad points. So let's look at this set for all points on the transport segment L, excluding their endpoints, the right endpoint L plus, such that the number of points on which there is discontinuity is bigger than 1. So there is so in other words, all x for which there is a discontinuity on each transport line. So so we can prove that gamma is supported on a graph of a map only if the set B, which is the union of all these bad sets, is a Berg measure 0. So that's what we have to prove. Take all transport segment, all points of transport segment for which the map is the monotone map is discontinuous, and see if they have measure 0. This is not so easy as it looks, because we can think, because on each ray there is only countable many points, and so that's measure 0, and you integrate, use Frobenio or something, and get it to measure 0. But that's not, this intuition is wrong. There are quantum examples studied by some mathematician, including Telly here, that existence of this joint interval in a square, there exists an example of this joint integral in a square whose middle point is a positive Lebesgue measure in the square. This is a very unintuitive example, but it can happen. So, so what we have to prove is, I will finish, I guess, tomorrow, but I'll just say what we need to prove is that really this is a set of Lebesgue measure 0, and here is the trick. So I will complete this proof next time, hopefully. Thank you.